hopefully not. Okay, let's see. I'm quite sure it's recording, right? So I yeah, should be okay this time. So so okay, like I guess repeat a little bit what we talked about last time. We talk about linear regression, right? Linear regression. So basically, so it's just trying. It's a really simple model that to fit some data, input data with what the desired output. So let's say I have like input vectors like x1, x2, xn, like n samples here. Let's say they are vectors, and let's say they have 1D output, like the desired output is y1, y2, and so on, yn, right? And we want to fit the model. So basically, like fit a linear model. So it can be like we want to have uh, yn or yi with approximately xi uh, w. W is just like the parameters. So W transpose xi plus some bias will be equal to that yi. So we want to fit this W and B such that this true, right, for all I, right? I1 to n. So, and we mentioned last time that more precise, more concisely, we can just introduce a dummy input and pad this thing, like so. Originally, I will have like W1 up to Wn, right? So, or then maybe I write it as a column vector here. W1, Wn is basically W, right? So now I can add one more parameter, like let's say BW1 and then up to Wn here. So this is my new W now. Maybe I put a W tutor here. Uh, and then I can have like X, like basically instead of Xi here, I have this new Xi here. It just pad a one here more. So I have Xi is equal to this is xi here. Xi here is a vector, right? So xi by pair one here. So then in this case, this thing will be shortened into like W tutor transpose multiplied by x tutor I, right? So then we say last time, like, if you go through some calculus here, um, okay, I guess the first thing I should say, like, what is the objective? Is like we want to make this close to this guy, right? So therefore, like, we want that yi minus w transpose xi, if I sum over all of them, sum I equal to 1 to n, I want to minimize that, right? And this is a should be the norm is small, basically the second norm is small. So, and the second law of the vector, then you expand that, then minimize the W. So then we can show that W is actually just equal to, oh, by the way, if we write this in matrix form, that in matrix form will be I have y as a big Y here. Okay, Y is a big Y now, Y1 up to Yn, and I have a big X here is basically padding my x1 tutor, x2 tutor, and so on, xn tutor, right? So if I have this shorthand notation here, um, actually, at that's fine. If I have the shorthand notation here, I should have something like uh uh maybe okay, I want to see if what kind of notation I use here. I want to fit with my notation here. So I use X a column, Y as a row vector. Oh, okay. I fit with the that's fine. Okay. Let me do just as what I did in the notes here. Um okay, in the notes I make this a row vector actually, I think. Right. Is that oh no, this is still a column vector. I make this a column vector. Yeah, that's fine. That's exactly what I did here. So okay. Um and I call this like yeah, in the notes that I call it X train here, but let me just call this X here. It doesn't matter. So then you look at this like I should have X transpose multiplied by W that I hope to be close to Y here. Right. So then I to solve this, then last time okay, this is just solving solving W for this is just a solve a um, least square error problem. Basically, the solution will be just a pseudo inverse. So W will be just equal to um, X, Y, X, X. Actually, maybe I don't. Oh yeah, okay. I use a notation at X, X transpose inverse. I think yeah, something like this. So then okay, that's basically your homework. I guess some of the guys I may have not sure about the homework. I by the way I posted a homework like yesterday, and for the third question, we'll be trying to do a very simple like uh, stock prediction, like basically using linear regression, or it's not exactly prediction because it's just I look at like how stocks are correlated. In that case, I just selected like several stocks and like try have you like try to predict like how Microsoft is related to all other stocks. Actually, you can have fun with that script and you can pull out more stock symbols like from there. Um, so but there like I split the data into training and testing. If you look at homework, like training, I remember it's like from last October to the end of the last year as the training data, and the testing data will be starting from this year. So for the training data, you use the training data to estimate W basically. So after you estimate the W, you can compute what is your prediction for the Microsoft stock price. Then you want to come basically like your prediction will be just W multiplied by your testing data, right? So you have testing. So I have a testing here, test, let's say, and this is a what you train here. Then it will be your prediction, right? Then you simply subtract that with the actual value, right? Then again, you compute the second norm or like some compute the mean square error um, of the entire vector. Then will give you the testing error. So, and if you replace it with the training X and training Y, then you will have the training error instead. So, yeah, I guess in one of the part I asked you to kind of like display both the training and the testing errors. So, any question with this?
Not yet.
Yeah, I guess if hearing none, then like we'll just continue with what we had last time. Um, so for linear regression here, but basically I just repeating like what I had earlier. So let me just continue. So um, I showed an example last time that is using the BMI kind of a silly dummy example. that is predicting. Okay, I forgot. I always need to pull out your chat box. Also, like just make sure if you guys have any question. So, um, he yeah, here basically the features I have height here, the BMI of someone, an individual, and also the age, and then I am trying to estimate its weight. Of course, it's a dummy problem because I know height and BMI. Actually, I know the weight precisely. I don't need the age here, but it's just a test whether stuff going correctly. So then I use this training data. Be careful, like just as in the homework, like because I want to absorb the B way, we always need to pad the features. So the original features only have high BMI and age, but I pad the one here, right? And I also like extend my weight here with another argument like B here. Then after I train the data, okay, I generate some training data like this, and then and also this the weights there. Then we fit that way, and I fit this. I got the I got okay. This is just going through the same thing. So I have the weight here should be just equal to the pseudo inverse somehow, right? Multiplied by the uh, y training vector there, and then in this case uh, if I play with this kind of synthetic data, I just have 30 data points here. I'm a standard deviation at 3 kilogram. Uh, we obtain this weight here, and as I mentioned last time, this is that's probably like that's one thing you want to check. Also, like in your homework exercise, you want to kind of like look at the coefficients there. For example, like I would expect, for example, Microsoft is more correlated to Facebook and Google. Most likely, it's not correlated to, let's say, Delta. So and that's what you're expecting. Like the weights there, like for example, if this is like for Facebook, uh, this will be like higher than, for example, like for the corresponding coefficient for delta. This one should be smaller. I mean, in this case, this third coefficient is basically the age, right? It shouldn't be correlated with the age at all. If you are given the BMI and height, uh, and so therefore, like it's quite reasonable if you I look at the weight. Uh, I mean, if I compute the mean square error, like the error is a 6.63 here, it seems a bit high. So uh, let's try to make a more complex model, like uh, to fit our data. So what can we do? So of course, I can really use a more complicated model, maybe uh, a neural network regression model, or I can use support vector regression. But here maybe I want to stick with the linear regression model. So what can I do? Um, so a something very simple is I may kind of extend my feature, right? So I have the original feature is the what's that the BMI, the height, and also the age here. So let me not just consider the feature itself, but also consider the products and the second order of the features. As I include also like the height square, the age square, and so forth, and also like the product of height and age, and so on. So now with this, I have a longer feature vectors here, and I can basically like I can consider this as my new feature, right? And I can train a new weight linear regression model. And my weight, okay, basically it's like very simple, right? Because I for the linear regression model, like uh, it's uh, again like that's everything is like analytic, like that's you have a closed form solution there. So I just need to modify my training data now. Now, instead of like original training data, if only these three values here, I also pad the extra values here. Now, then I modify my X matrix, then I can compute my uh, new W. So, and now I can recompute my training error. Now my training error is smaller, it's nice. And I can repeat that. Like if I'm not happy enough, I can make it an even higher order. So instead of like just end with second order, let's also include the third order terms, third degree terms, or like I don't know whether I should call it order or degree. So and then in that case, you can just verify that like the number of features will increase to from 10 to 25 now. And now my mean square error isn't even smaller than 0.32. And I can continue to do that. Like fourth order will give me, wow, the mean square error just like, okay, super small. Um, but the problem is like, you cannot just look at the training error. You should look at the testing error. I mean, it's the generalization that is important in machine learning. So my training error did drop like when I increase the degree or the order of the features like from 1 to 2. But then like when I continue to increase that, my my training error did drop, but my testing error raised like rise actually it rise very quickly, even if like to a fourth order, like it get really bad. Um and anyone know like what's the problem of this? Like, do you know like the name uh of this phenomenon? That's the name of the phenomenon in machine learning.
Is it called overfitting?
Yes, exactly. This is you're overfitting the your data, and that's something like you want to avoid. Uh, and let me give another example, like to illustrate that why we have overfitting, or like, where does that come from. So let's consider like a even simpler problem. I have curve fitting here, right? I have this is like the original curve that is like this, but then like I have sampled some data point on the curve, but also like my sample is noisy. So you see like some of them is getting like higher or lower from the original curve. Now then I try to fit this data. If I use a linear model to fit this data, then I will have a line like this blue line like this, but apparently it's like quite far from the original curve. Um, if I use a second order model, it's just like what we did earlier. So I can still use linear regression, but in this case, like my features, like okay, by the way, like if I fit this data with linear regression, my feature would be just one value, right? Because like the feature is just like the x-axis here, like the x location here. Of course, I also have a dummy feature one here, uh, and when I kind of increase to the second order, now besides like x and one, I also have x square here, and then it's getting better. Like I can continue to increase like a third order. It looks a little bit even better. Is that I don't know. It looks similar though actually, but and as I continue to increase, it's getting not better now. Fourth order is still okay, but fifth order, like you see like some overfitting problem. Like this, like when I get beyond the range here, or like the sample points like that the support here, then it's getting there deviate from the original curve quite a bit. So if I continue to increase, it's getting really bad. Yeah. So that's overfitting. Uh and by the way, the opposite of overfitting would be underfitting. That's basically the case when I'm just fitting a linear model that is apparently is a quadratic. So that give me also like not very nice result. So in practice, like of course you want to get into like somewhere here, like not overfit and not underfit. By the way, there's a caveat here that like this is the classic uh kind of explanation in terms of bias versus variance in statistics and also in machine learning. But there's some new results like just a year or two ago. So everything you find in textbook basically will explain like just what I'm telling you here. But I will give a caveat like later on that like what we talk about is probably not completely true. So so this is just a summary of lesson learned, or I say, wait. So we want to, okay, this is a classic textbook, like we want to like avoid overfitting and underfitting. So and know that like the only you cannot know like whether you overfit or underfit, right? So in practice, like when you have a machine learning problem, what you're going to do is that you are going to split your data set into like 3 pieces. So you have the training part, and then the validation part. Sometimes people also call this development set, dev set. So it's more fashionable. It sounds more fashionable in kind of like software engineering maybe. And that's also like that's the testing set, the test set. So so what you will do is like, for example, if I need to consider which degree is optimum, like which degrees give me best result in this case. So what I'm going to do, I will just say for each of the degree here, I will I will train the data using the training set here, but I'm not going to test my model with the training data, but I will kind of like estimate how good my the result from my validation set here. So I use my validation set to get the performance for like each of the degree value here. Basically, I use my validation set to plot this green line here. And then eventually, finally, I will, let's say I selected this one is actually the best here. Then I will use the test set to actually to uh, approximate my testing error. So here, like I skip the validation set here because yeah, it's just for illustration or understanding. I don't need the validation set. But when you are actually submitting maybe paper or like yeah to journal and conference, make sure you split into training and validation and test set. Like definitely your reviewers, I mean the reviewers will raise concern if you don't split into validation set and test sets, because then your testing error is like um will be overly optimistic, because I yeah, if you don't you basically you're testing if you're training set or something like if you're testing with your training or validation set, you will be overestimated over optimistic. I mean your result will be over optimistic. So okay so there's some other remark here. Uh, basically, like if you make a sufficiently complex model, like you're able to learn everything. Okay, that's actually also like uh I need to put a kind of like a caveat here that yeah, this is also old school thought as well. Like at least I don't know, because the textbook will say that, like, but uh I need to be very careful with like what I'm going to mention also, because like that's his new result, and I'm not sure like it's completely verified by different groups. Um, and another remark is like if you do what machine learning is very similar to optimization. Actually, the this the way to do training is exactly doing optimization, right? But just like unlike optimization, we don't actually have the true objective there. We have an approximate objective function that is constructed by your training data. So, um, but essentially, you can think of it as just an optimization problem. So I mentioned earlier, you don't want to overfit and underfit. So, and also like this overfit underfit, like they there's also another jargon that people talk about like often is a high bias and variance, a bias versus variance, a trade-off. So we say like the model has high bias. You can think of it just someone is high bias, like he is very rigid, then he's not able to learn new things. So he's a kind of like, in this case, he cannot bend, basically. He cannot uh, uh, kind of like cannot really adapt to the data. So that, oh, okay, maybe just a, so which one? Okay, so okay, this make it a quiz question. Just make you guys, I'm not sure you guys are actually following. Um, so if I am high bias, am I in this region or this region? Am I in the underfit or overfit region? Yeah, we have mixed answer. That's nice. So it actually should be underfit because your model, think of like that example, like the high bias case for the curve fitting will be like I'm trying to fitting a linear line on a quadratic data basically. Now I cannot basically, impossible to fit the data into my model because my model is basically too rigid. So it is therefore in that case it's actually the underfit case. So the other case is the, oops, yeah, it's a high variance case, is a basically the whole overfit case. So high variance meaning that like your model is too elastic. So basically, um, someone doesn't have have a stand of anything. Basically, based on any data, he just fit his opinion based on that data. So therefore, like your data, if you variance, like high variance, the variance here meaning that like if I give you different data, you will give me different training model. So therefore, like if you think of this overfit region, like what is happening is if I going back to this one here, if I have this data here. So let's say next time if I sample like differently, if or maybe I take this case, like this cup overfit case here. If I sample differently, maybe I have a sample point here instead of here, then my curve will immediately become this way. So, and each time your model, so of course, like if your curve become this, your weights there, like your model parameters should change quite a bit, like should be quite different. So therefore, like if you have every time, of course, like every time you sample the data because of the noise, supposedly will be a little bit different. So if you have a in the high variance region, or the model is, yeah, if the model is too elastic, then every time you will have you can result in a very different model, trained model. So therefore, like people call it high variance in terms of the model parameter. Um, and let's see what else. So, and of course, like, the model complexity is like depends on your data, right? So the complexity of the problem. So you cannot beforehand like know how high the capacity is needed. So again, you need to go back to again split into like training, validation, and testing set, and see like what model capacity is sufficient for your problem, basically. Um, Another way like of kind of not increasing. Okay, what I'm saying, like I want to increase the number of parameters, but at the same time not to have the model to be too easily overfit. in that case, people can apply regularization. So regularization is my interpretation, my understanding would be like you have the parameters, trying to restrain the parameter a little bit, like not to make it running wild. And if you do that, then you can afford to have more parameters. And usually, if you have more parameters, have a more complex model, you tend to have a better trained model. Um, and it's often like, but it's not a must, but like it's often that like you have a regularized, more complex model is performing better than a simple model that is not regularized. Um, and a simple regularization, for example, for a linear regression model, I can use something known as the ridge regression. So basically, instead a loss function, hey, remember this is the original loss function. This is just saying the minimize the mean square error, right? So this is just a mean square error of the data. This is again the data matrix, right? So I just say this is essentially the second norm here. Now here I add the this a lambda w transpose w, but this is actually just sum of square of all the parameters, right? So this like one half, you don't need to worry too much about that. This scaling factor just make it look nice, because when you take gradient, this thing here, the gradient with respect to w, just this guy here will give me 2w, right? So we want to have one half just to cancel the 2 there, just make it look nice. So this is a ridge regression, and by the way, using ridge regression, the nice thing here is you still have the closed form solution, because I add this here. I can combine this guy into this one here, right? Just do some algebra. I can absorb this W transpose W into let's see. Uh, I expand this guy. Yeah, I expand this guy. Then I will have this term here, like for y multiplied by y here, right? This one is a w x transpose w transpose multiplied by this one here. I might have let me erase this, right? And I have y transpose multiplied by this guy. I have this guy here, and then I have this one multiplied by this one will be like w x transpose w, right? Now I can absorb with this guy here. I have this guy here, right? Then my loss function will be replaced by this one. Then like last time, I can take the gradient. If I take the gradient, then instead of having just xx transpose multiplied by w, I have xx transpose plus lambda I plus multiplied by w. And so then the solution for that is very similar to last time, but note that like I have a basically this the inverse here. Instead of xx transpose inverse, I have xx transpose plus this lambda I here. So I mean, you have the regression here, but sorry, you have the regularization here, but you don't really need to do have any additional effort. Like the ridge regression is very simple. I still have a closed form solution. I probably in the next homework I will ask you guys to just test also like the ridge regression for that problem. Um, Another very common regularization is known as the Lasso. So here, note that the ridge regression, I'm adding the sum of square of all the parameters, or like the second norm of the parameter vector. So here instead, like I can consider the first norm of the parameter vector. So I add the first norm. The first norm has the effect to um, give you a sparse solution. Therefore, like it was quite popular, like 10 years ago, I guess, when people like to talk a lot about like sparse coding, like compressed sensing and so on. Like they want to get a sparse solution of the whatever the estimated parameters. So you can use kind of add a first norm penalty here to kind of obtain a sparse solution. And again, like this first norm will be just like sum of like instead of sum of square will be sum of the absolute values. But actually, in this case, like Lasso, unlike the ridge regression, you don't have a closed form solution. But actually, it's quite easily solved still. Actually, what's going on is that you can solve it with like iterative soft thresholding. What does that mean? Is like I do not have a closed form solution, but I can find the gradient of this guy rather easily, right? But there will be like two cases. It will be depends on like whether each of the element of the each component of W is whether it's positive or negative. For example, if I consider this guy here, the entire loss here, if I just compute the partial derivative, let's say with respect to the first parameter, like W1 here, then this part can be easily computed. Right? Let me just for simplicity, I call this FW here. So if I take the partial derivative of this thing with respect to W1, I have like partial F W partial W1 and also partial this lambda partial absolute W1 partial W1, right? Oh, sorry, this is like the first norm. That's basically, be careful, like this is like different things here. So I will have like basically two cases here. So let me put it out here. So one case is like if W1 is positive, right? But W1 is positive, then I will have just equal to partial F W partial W1 plus lambda, right? And if it's negative, then I have partial F W partial W1 minus lambda. So it's impossible to get a closed form solution right away. I cannot just set this to 0 and then find the W because of this. I have two different cases, but I can do like steepest descent. Just actually, for most problem, eventually it will be like just doing like optimization with steepest descent and it's like variations. So in that case, I can have like W, right? I want to have like the loss is smaller, so I will have W. The next W, let's say like W, let's say I compare to A to AW, I have like previous estimate of W, like Wn, let's say. And I have the next W n plus 1 will be equal to Wn minus the slope, right? So this is the slope here, right? This is the gradient, let's say, minus del LW, let's say with some step size T here. So, but the tricky part is I have these cases, right? Two cases here. Sometimes it's positive, sometimes negative. But I can split this into two steps. Basically, I can split this into this step here into, maybe I write in a different color. I can have like W n plus 1, or maybe I call like W tilde, like a temporary W, will be Wn minus T delta W. So instead of L, I will just say delta WF W here. So I just take the gradient of the first term here, and then I will do a so-called soft thresholding. So will be like Wn plus 1 is equal to W tilde minus T lambda W yeah, this is actually I need to write in case wise actually. I mean component wise. So for the ith element of this vector wi, uh, the ith element of wn plus 1 will be equal to wi tilde minus t lambda when wi is bigger than lambda, bigger than t lambda. And if wi tilde will be otherwise will be if wi is less than t lambda minus t lambda, then we'll add t lambda. Basically, the effect is something like this. Let's see. I will have this soft hassle, then will be something like that. Oh, wait. I should write like this. Yeah. So if your the value is say original value is say here, right? So here like this over here. Listen. You kind of like push it down, like when it's positive, larger than t lambda. And if it's a negative less than minus t lambda, you will push it up. So you get more likely to be zero, basically. So and that's why you see why you get a solution is likely to be more sparse, because when values that is close to, I mean, within the range of minus t lambda and t lambda, those values will all become zero. So
Dr. Cheng,
yes,
when you say a sparse solution, do you just
yeah.
mean that there's more zeros?
Yes, it will be
Okay.
more zeros. So you get a vector that will be have likely to have a lot more zeros.
Okay.
Yeah, and this is something like attractive, like in yeah, especially in terms of yeah, at least like computation right, it'd be nice, right? Because if you have a sparse solution, the values that doesn't have, I mean, as long as it's zero, basically you can ignore them. But there's other benefits, but I'm not going to that. Yeah, like, but as I mentioned, like 10 years ago, a decade ago, it's very popular, or like I should say, a very hot research area. It's still useful, but it's not a hot research area anymore. Like people work on something along like complex sensing. Complex sensing. This is all this kind of idea basically, and yeah. So anyway, and this is Lasso. I just ask you guys to try Lasso as well, like in the next homework. But you for that time, I don't need you to implement like this. I guess you may use a scikit-learn to train your model. But for this assignment, I really want you to do from scratch, like because it's so simple, right? So it's just like pulling out the W, like you can write it in closed form, and at least also like give you some exercise of like playing with matrices in whatever like PyTorch or NumPy that you use or select to use, because yeah, that is kind of some important basic, I guess. So here is I just showing that like, okay, if I use ridge regression and also Lasso, let's see, this one I pick lambda. Like for both cases, I use yeah, use the same lambda for ridge regression and Lasso, and I have the blue curve is let's see, blue is the Lasso, and then the green is the ridge regression. Try different value. Of course, like this comparison is like you the lambda here for Lasso and ridge regression you can expect like they have different meaning because they are consider different norm, right? So probably it's not a good idea to put in this. You say, for example, here you just say, okay, ridge regression is doing better than Lasso because like it may be there have some parameters that which regression is doing better, but it's just say for this particular parameter, it may not be appropriate for which regression. But for convenience, just put it like this. So see like the effect if I change the parameters here, and as I increase the parameters, that, oh, wait a sec. Oh yeah. Sorry, I'm thinking like why it looks like more and more overfits. It should be other way around, right? So that's why. So I increase the parameter. It should overfit less. Yeah, I'm actually still like you see in this case really Lasso is doing better than rich regression. I think you can try more, maybe like even higher lambda, see if like rich regression will catch up. But in this case, uh Lasso appears to be better. That um fit better to the original curve here. So okay, anyway, like this is again just repeating a little bit what we talked about earlier. So and we can have regularization. We also like demonstrate what's regularization. Um and yeah. And that's the caveat I want to bring out. This is a rather recent paper. You can click on that. I mean, like you know the slide, right? You can click on that and find the paper. It's like paper last year. So the argument is like this is like the classic textbook explanation that people look at the overfit and underfitting regime. But that regime is like basically the number of parameters or the capacity of that model, or you can find the number of parameters of the model is less the number of the training data. That's typically what people consider. And they find that like if we continue to go beyond that, basically the number of parameters is like larger than the number of training samples, then you will get to this like over parameterized regime that actually continue to go down for your training for your testing error. So of course, when you go here, go to here, for the training error, like your training error will always just go to zero. That's at the point that you're supposed to overfit. When your number of parameters is like more than the number of the data point in the model, then of course you will overfit the model, right? So, but yeah, overfit the data, right? But if I continue to increase the number of parameters, I'll continue to overfit that. What they observe from the experiment is that you peak here, like somewhere, and then but if you continue to increase the number of parameters, you will actually drop, like the testing error and drop. So this kind of explain why neural networks work, because it really working on this regime that like you are oftentimes over parameterized. And on the other hand, for most classical approach, is working somewhere here, especially SVM and so on, that you have far fewer parameters than the number of training data. Yeah. So, but of course, as I said, like this is like something rather new. I don't know like whether it's verified from you. You can look at the paper, um, and decide whether like this is a you trust it or not trusting it.
What is the paper?
Oh, if you have the PDF, okay,
I
you can
do.
click on this. If you click
Oh,
on
I
this,
can click. Okay.
yeah, yeah. So
Yeah, it worked. Thank you.
yeah, so but I don't know. Maybe like several years later, maybe like it's people discover something different. Like from I didn't kind of like take up the follow up work. I don't know whether like someone kind of individually verify the results. Yeah. So this I okay this basically conclude what we talk about for linear regression, or like in general for a regression. Now talk a little bit about like classification. So I for classification, like so you basically have a binary label on like I should say binary discrete label, right? So for example, I can have a binary classify an image whether it's a cat or not a cat. So that would be like binary class, just yes or no. And And I can create a binary classifier just as what I did earlier using regression, uh, just like adding by adding a kind of a something similar in a neural network or a artificial neuron, a activation function, right? So in the sense that, for example, I have this image here, I can just do like as linear regression earlier, but now I have kind of like a activation function. In this case, would be just a step function. So determine whether this is a larger than zero or less than zero. So it's larger than zero, then I will get one here. Then I will decide that it's a cat. Or if it's less than zero, it will get zero. Then it's not a cat. So in this case, really, this is exactly when I'm doing a linear classification like this. It's nothing but just a single neuron. Right? I have basically a single neuron that with features. Then I have weighted sum all these features, and then I have a activation function, and I have the output here. And by the way, this is also SVM is doing. SVM is exactly doing this, but just a SVM is a doing. I mean, support vector machine is a more kind of like careful or like more intelligent in kind of like finding the weight here, the optimum weight here. We'll talk about that maybe next time or sometimes later also. Um, and sometimes this like this stuff this function I earlier this activation function is sometimes also known as the scoring function. And earlier I use a step function like just to do make a hard decision. Often it's even better if I use a say a logistic function, so or a kind of sigmoid function, in the sense that I just move out this step function. Because if I use a logistic function, then presumably I can obtain not just like whether it's a cat or not a cat, but I also like can, if I train the model well, I can get the probability of like whether it's a cat or a cat, not a cat. So maybe if I train the model really well, uh, the outcome of this model can precisely give me the probability. When it's like very close to one, it's say like it's high probability it's a cat, and when it's close to zero, it's like high probability is not a cat. And if like 0.5, there's no idea whether it's a cat or not cat. Um. So let's see. Let me okay. Before I talk about cross entropy, let's look at multicast first. So let's say now if I want to classify not just a cat or not a cat, maybe I want to classify whether the image is a cat or dog or like sheep, then I can do the same thing, right? I can still like do a linear classifier that I will have basically getting score for each of this component here. Wait a sec. Yeah. Or by basically multiplying your input here, like I have the input first factorize the input here, and then multiply by the weights, right? The weights corresponding to a cat, and the weights corresponding to dog, and so on. And after multiplying that, I want to scale that like into probability. So the way to scale that is I can use, instead of the logistic function, I can use this so-called softmax function. So what it does is basically I will have this score here. When it's like the score is higher, then it's like more likely to be that object. So I will first take the exponential of this value. So I want to use that. Yeah. Uh, so I will take this guy here, exponential that, and of course I can exponential this guy like with yeah, but that's okay, like with some part, yeah, it's okay, forget about it because this can be adjusted here. So I do exponential that, then because I need to normalize this will be supposed to be probability, right? So I should be normalized by one. So maybe like this, I have let me just write this. I have like weight cat, right? weight cat, like multiplied by x, and then I have weight dog. Let's say the probability of cat, probability x is a cat, will be like exponential of like WC multiplied by x over exponential WC multiplied by x plus exponential WC, sorry, WD, let's say the weight for the dog multiplied by x, and exponential weight ship multiplied by x, something like that. So here I also show the softmax function. It's just this. Now then for training, like it's very similar to as before, right? So the training will be, we want to design some score here, or like design some loss here, such that like whether your classification is good or bad compared to your ground truth. So let's say I have the probability I computed here, like the estimated probability for cat, dog, and pig, right? So now let's say I have two cases here. Let me just also sketch another case. Okay, I guess I make it another question here. So this is classifier 1. Let's say class 1. This is classifier 2. Okay, maybe first ask a very silly question. So does classifier 2 did a correct classification? So I'm not sure. Okay. Maybe I ask the second question before I answer. Like, that's actually interesting question. So okay, you're thinking there's a threshold. Actually, for this kind of cases, typically we don't have a threshold, but we just pick the class that is highest as our estimate. Yeah. So let's say question 2 or question 3. I guess this is also should be which class is better.
Which class is what?
Yes, I guess it's pretty obvious, right? So this will be better, even though like both of them classify correctly. Both of them we decide, okay, the actually is a dog, but this one is better because it's more certain it's dog, right? Compared with like this guy, maybe I don't know this value, so maybe it's 0.7, and maybe this is 0.4, maybe I don't know. In this case, it's still considered as a dog, but like this is smaller. And so basically the problem is like, okay, if I have these two cases here, like how do I quantify like this one is better than this one here, because both of them is actually give correct classification, right? So what we usually people do here is actually most often like what people do is we can consider like this is like the correct classification here. This itself is like a distribution itself, a distribution, even though it's a delta distribution that like if I know it's a dog, then it will be have one or yeah or one for the Q dog here, and for all the values for all the rest of the classes will be 0. But like these other cases, you can think of this as a distribution, right? So what we can do is that I can compare distribution. So let's say if I'm able to quantify like how distribution differ from one another. If I'm able to say this distribution is closer to this distribution and this distribution is not as close as this distribution, then we'll be able to quantify that, right? And the classic things like people does using this so-called KL-divergence. So the KL-divergence is basically defined like this. I have like, let's say this is like the Q distribution. I have the P distribution. Again, like, okay, this is KL-divergence. It's like compare to distribution. So whether they are similar or not similar. So I will have like, for example, like KL, Q, and P. So this will be like how different these two distribution. Basically, if like these two distribution, if the same, I will have KL-divergence equal to 0. If they are not the same, they will be like larger than 0. So the precise definition of the KL-divergence is something like I have like Qx log Qx over Px. So I have x is the elements, basically the elements in the distribution. Maybe I put in x here. And so first of all, I know that if I have q equal to p, then apparently this will be equal to 0, right? Because for inside the summation here, like all the terms here will be equal to 0 if q equal to p. So therefore, if two distributions are identical, then the KL-divergence is equal to 0. And at the same time, we can show that, let's see, maybe I find some space I can write more, maybe here. We can show that like the KL-divergence is bigger than equal to 0. So I can have KQP. This is always bigger than equal to 0. So consider that like my KL-divergence is like QX log QX over PX, sum over X here. And consider this simple inequality. Let's say if I have a log function is something like this, right? Say like that. Oh, okay, like that. It's very hard to sketch here. Okay, this is difficult, but anyway. Maybe I draw the line here first. Oh, this is pretty bad. Hopefully you understand what I'm drawing. So this one is let's say y is equal to x minus 1 here, let's say. And this is the y is equal to log x. So note that like this line y equal to x minus 1 is always on top of log x. It's very easy to verify. And they hit each other, basically it's like tangentially hit each other at x is equal to 1 and y equal to 0. So therefore, like I will have an inequality that like x minus 1 is bigger than equal to log x. And basically, the equality hold x minus 1 equal to log x if and only if x equal to 1. Now I can take advantage of this simple inequality here to show that like this is always bigger than equal to 0. So I have like qx log px over qx. So I have like just flip the numerator and denominator, it give me minus sign here. And then note that minus log, we have like log x is less than equal to x minus 1, right? So therefore minus log x is bigger than equal to 1 minus x. So I have this is bigger than equal to x qx 1 minus px over qx. And then this will be just equal to x qx minus px, right? Or then maybe I write the summation out. But note that like both qx and px are distribution, right? They both sum up to 1. So I have like 1 minus 1. So this is equal to 0. And I'm note that like for this inequality side, like the equality hold only when like this only when what? Only when x is equal to 1, right? X equal to 1 is basically px equal to qx. So therefore, like I have like KL-divergence here is like always bigger than equal to 0 and only equal to 0 when like p and q are equal. So they have the same distribution. So now using KL-divergence, then I can design my cost function will be basically, let's see if I have written here. Okay, this is just repeating what I said. Oh, okay, I have a sketch, it's much nicer. So anyway, okay. So in actually, like more often, like when you play with the machine learning library, PyTorch and so on, you don't see they actually use KL-divergence, but instead like they like to use cross-entropy because like they are the same, but like when you expand the KL-divergence, basically I have Q and P here, my KL-divergence is equal to this way, but I can expand the two terms here. I have like minus Q log Q here, and I have like Q log P here. And the later term here is like actually the cross-entropy. And the first term here, like Q log Q here, I don't care about Q log Q because I'm optimizing over P, right? Q is like ground truth anyway. This doesn't affect the design of my model or like how do I train the model. So therefore, like in practice, people don't use like KL-divergence. Like we can ignore that. We just use cross-entropy here. So and the cross-entropy is just equal to this guy, minus Q log P here. So any question? In case like if you're ground truth, for example, you can have like more complicated label. For example, like I can have like labels that I cannot 100% say it's a dog or cat. I don't know whether you have images say that. Then maybe I have like 90 upon 9 is like I think it's a dog, upon 1 is a cat, and like 0. Like maybe I have a label like this, the ground truth like this, then I will have basically I need to consider all the classes. But however, in practice, and most of the time I don't have ground truth like this, right? I always quite sure this is really a dog. It cannot be a cat. And so therefore, like in practice, it's like the Q is usually is a delta function as we mentioned earlier. So then like this can even simplify further equal to this. So this JX here is basically the class of the ground truth class of the input X. Yeah. So it's, um, but yeah, don't worry about too much this symbol anyway. Um, let's see what I'm waiting here. Yeah. Yeah, I just put in also the yeah, let's skip that. I don't think it's a important. So um so optimization, okay, maybe I'll skip the optimization part here. So or like actually I already mentioned a little bit of that, right? So I have the weight there. I can optimize the weight as long as I can find the gradient, then I will just if I can find the gradient, I will just uh going down uh going down slope. So to just going along the direction of the gradient. There's some variation that we will mention more, like maybe in the future, like several class later, how to do the optimization. Um, this I probably will skip it for the moment as well. Like uh, for the softmax loss, like the derivative is pretty nice. Yeah, but I will talk about that more like when we talk about uh, backpropagation. So I will first skip this. Maybe a remark like for gradient design for the moment. Uh, they have this so-called stochastic gradient design, just meaning that like because like you have the training data. Uh, what I mean is that you have a lots of training data, right? So you have lots of training data. Um, you have so many training data, like often you cannot load all the training data at one time. So oftentimes you just say train a model with a batch of the training data. So with like just some, this is a long X, I have like to take it the first batch here. And then with that, I train the model. And then afterward, I take another batch and then take another batch. Um, and this is only the mini batch gradient design. And when people say stochastic gradient design, like it's actually mean that supposedly, like technically speaking, it should means that the batch size just one. So every time you take one sample to build your model and going down the slope. But in practice, like people, or like I shouldn't say in practice, I mean, but often when people say stochastic gradient design, they don't mean that. They actually mean the mini batch gradient design. So, but just a remark there. Uh, moment I will skip that. Like I will come back to that later on. So it's just like introduce moment will get you optimize a bit better. Um, for the gradient, like you can compute numerically as well. Uh, apparently, for example, uh, if I at a point here and I want to find the gradient, uh, for example, like gradient will be like the partial derivative with each of the uh, each of the component, right? So let's say I want to take the derivative with the first component, then I can just approximate the partial derivative like this, right? So I can have the loss, my input like vary by a small h, and then I subtract like without the small h, and then look at the, I mean, divide by the step size. So this is just, I mean, the basically the true the real definition of like the derivative, right? When your h goes to zero, I mean, you take the limits to zero, but of course you cannot take limits to zero. You can take a small h, but that will give you approximation of the gradient. So um, if you yeah, actually this is a good idea to for you to verify results. For example, you want to see if you do things correctly. Is it's good sometimes like when you're really stuck and they have don't know where is the bug and you suspect that maybe the gradient is not doing correctly. Yeah, you can try to do the macro things just to make sure things is correct. Um, and so Okay, I guess I probably stop here. Next time I will talk about SVM. So I guess I will just stay for like a couple minutes just in case if you have any questions. So I guess there's someone is speaking. Yeah.
你这16 GB 的，
我猜应该有，
里面有多少东西啊？
你要照盘是？
对，我
Um,
首先给你
Guys
拷
in
出
the
来。
same room?
Dr. Cheng.
Yes.
So I did have a question, just going back to the very beginning of the lesson, and maybe I should have asked it then, but
Yes.
when you were talking about the training set, the validation set, and the test set,
我原来一直问完
so I don't know who's talking.
Yeah, maybe I mute him. Like, oh, okay.
Okay.
Yeah.
I've been wondering what is really the difference between the validation and the test set, because I know when you're running your validation, right, you're not training your model on the validation data. So my question, I guess, is why can't I just use validation set as test set?
You can if you're not submitting a paper.
Okay.
Because like typically what you're doing like is like you propose a new approach, right?
Mhm.
And then you say you want to say compare your result with like someone else, right? Your approach, right, with someone else. So if you use your test, if you use your validation set for testing, then you're kind of cheating. You can think of you. It's not obvious
because I can
Yeah.
change the model.
because
to
the model already see the data like ahead of time.
Yes.
Yeah. So
Okay,
like,
that
that
makes
would be like a
sense.
bias. Yeah. Yeah.
But if it's just for like a specific application,
Yeah.
you
If
know,
you're
maybe.
just playing with like for yourself, like that's fine. But like
Yeah,
if you
okay.
eventually need to report stuff, like for example, writing a paper, or like you report to your boss that I have this model and I get the testing errors like this. So you should like split. You have to.
Okay,
like,
I
test
should
it.
then. It's
Yeah.
good practice. Okay.
Yeah.
And then my only other question is, I'm just starting looking at the homework now,
Yeah.
and I opened the Jupyter notebook,
Yes.
and I scrolled down to this part that says append a dummy variable to the training and test sets, and by dummy variable.
Let me open that also. I forgot like what a sec. If I can open.
Yeah, Vishnu, I thought maybe it was the bias as well, but I just wanted to make sure.
Let's see. Pull my windows on this side. So you mean the third question, right? Is that right?
Yeah, click on there, and then if you go in and scroll down to the
Yeah.
append a dummy variable. I know like you were talking about incorporating bias into the weights by adding a 1. Is that
Oh yeah,
that...
yes, that's the one. Yeah, the dummy feature is the one. Yeah, you have to
Okay,
append one there. Yeah.
gotcha.
Yeah.
Thank you.
Yeah. Okay. So I guess I will see you guys like next week then.
Okay, bye.
Assuming you guys have no more questions. Yeah.
Thank you, Professor.
Yeah. See you guys.